So a good student is someone who is used to the following situation. You have some challenge, which is the course material. You study the challenge. It may take more or less effort, but it's a finite amount of effort. Once you do this, you completely dominate the thing, and then you go to the exam, you get good grades, and you continue. Okay? Research is not like that. It's completely not like that. And so people who come from that background, they oftentimes have a hard time because they have not had to struggle, at least academically. But the point about research, is the way you make a lot of progress is, you need to try a lot of things, and a lot of them will fail, and then you try the next thing. And the fact that you fail doesn't mean you're dumb. It means that you try something and it fails, so you need to keep trying. And if you keep trying, not only with each try, even if you fail to do whatever you wanted to do, you get better and better and better, even if you don't realize it. And eventually what will happen, for instance, if you're a PhD student, is you start doing things on your own, and at some point you have a very cool idea, and it was done by someone in the 60s.
The guest of today's podcast is Dr. Miguel Montero. He is a theoretical physicist at IFT Madrid, working on string compactifications and the Swampland program. So let's talk to Dr. Montero and listen to what he has to say. So, Dr. Montero, welcome to the podcast.
Thank you so much.
So before we talk about anything else, can you tell us about the projects that you're working on right now?
Okay, so as you said, I mostly work in string compactifications in the Swampland program. So the Swampland program, broadly speaking, is what we're trying to do is identify the universal properties that consistent low-energy effective field theories must have in order to be, successfully embeddable in a consistent model of quantum gravity, such as string theory. So it's a very, very, very fun thing to think about, because it forces you to learn many different things from different angles. So to be a Swampland researcher, you need to certainly learn a bit about particle physics, a bit about cosmology, and certainly string theory, string compactifications, holography, because all of these are tools by which you might really be able to learn anything about quantum gravity. So for instance, one thing that we are looking at is what are constraints that you can get on vacuum energy from general symmetry principles in string compactifications. That's something that we were just discussing just a few minutes ago. And I also do work in sort of like more, on one hand, Swampland is about trying to identify universal constraints. But the other thing I do is try to find concrete models in string theory. And so, for instance, one thing that we are very excited about, that we are close to finishing, is we're trying to find solutions in string theory which are very much under control and that give rise to accelerated expansion.
So what kind of symmetry principles are you talking about when you say that, you're trying to constrain the vacuum energy using symmetry principles?
So there's this kind of symmetries in string theory and field theory, actually, that have been all the rage recently. These are called non-invertible symmetries. Okay, and in string perturbation theory, you can use them to constrain some couplings. So there are interesting symmetries that are broken by loop effects, but not at tree level. So they can generate small couplings naturally. And so we're just exploring whether one can do anything about vacuum energy from that point of view. There's been already some papers that done something like that, and we're just trying to understand those more systematically. But it really is just ordinary internal symmetries that are broken by loops, but maybe they are approximate at tree level. So I can generate small couplings.
I see. So you already mentioned the Swampland program, and you kind of also mentioned that what it tries to achieve. But if we just go into the details of what the Swampland program is, can you explain to the audience that what is the Swampland program, what is the motivation behind it, and how do you come up with the, what are called the Swampland conjectures? So if somebody wants to come up with a new Swampland conjecture, what kind of things that Swampland conjecture has to, satisfy in order to become a conjecture?
So the question is, why do we expect that you can do something like Swampland, general principles? Well, in fact, the expectations you might get if you're a low energy effective field theorist or a particle physicist, really. The naive expectation you might get is that there's really nothing much that gravity can say universally at low energies, and that's simply because, well, not only gravity is very weak, it's not so difficult to construct at the classical level. It's very easy to take your favorite quantum field theory, whichever you like, and couple it to gravity. There's for those people listening to us that have a bit more of a physics background, or if you don't, just go to Wikipedia, Einstein-Hilbert action, and look for coupling to matter. If you want to couple any matter to gravity, it's very easy. You just put square root of minus g in front and change derivatives to covariant derivatives. So a classical level is very easy to do. Now, what we have been learning recently, and that's sort of like the core of the Swampland program, is that quantum mechanically, this is not the case. It's not so easy to do this. And why is that not the case? It has to do with general things, general properties that we would like to have in a consistent physical theory, like unitarity. So we would like our probabilities to always add up to 1. Doesn't make sense. If you tell me you have a model for a coin flip where the coin has 50% chance of heads and 70% chance of tails, that makes no sense, right? If it's 50 heads, it's 50 tails. If it's 30 heads, it's 70 tails. That doesn't make sense. So that's an important principle. It's something as, it might sound stupid, that is something that we would like to impose. And of course, we don't get anything new by thinking about probabilities adding up to 1 when we're flipping coins. But if we're thinking about more interesting processes, like things like black hole evaporation and the like, demanding unitarity, demanding that the evaporation takes like that, can give constraints. And a lot of Swampland arguments are based on, for instance, of expected properties of black hole evaporation. So for instance, one of perhaps the best established Swampland conjecture, which is this idea that there's no global symmetries in quantum gravity, has a lot of, heuristic arguments based on black hole evaporation. So behind it, so for instance, you could imagine that you have some global symmetry, a particle with a global charge, you throw into a black hole, then the black hole evaporates and the charge is gone. So that means that the charge is broken by quantum gravity. And that's something you perhaps would not have guessed from a field theory point of view. So that's one of the sort of like, these heuristic arguments based on black holes are perhaps why we think that maybe Swampland ideas are general and they apply to any quantum theory of gravity. But then of course we have more. We cannot prove them in general, cannot prove them in, because we don't have a framework to prove things in full generality in quantum gravity yet. But we can prove them in particular corners where we have more control. So for instance, one can give a proof there's no global symmetries in perturbative string theory. And there's arguments for it as well, very good arguments in my opinion, using holography, using the AD-CFT correspondence. So these are two cases where you can prove them. And there's one more thing, one very important thing. You were asking, suppose I want to do a new Swampland conjecture, what do I need to do? Well, it's very nice if you have a black hole argument, but maybe that's hard in your case for whatever conjecture you have, so maybe you cannot do that. It's very, very nice if you have a proof. Of course, if you have a proof in this particular subset, it's very nice, but then people might still doubt, maybe it's true here, but not true elsewhere, so on and so forth. But those things are acceptable not to have, it's like, as you were saying, it's like we are sort of still at early stages of learning what quantum gravity is in the non-perturbative regime. So there's many stuff that we could do. The one thing that you should always have, always have, and is the most important thing, is that whatever conjecture you have, it is supported by as many examples in string theory as possible. Why string theory? Well, there's perhaps other models for quantum gravity, but string theory is the only one so far which is so developed that you can ask quantitative precise questions. And string theory has, about the low energy effectively theory, and string theory actually has a very large landscape of solutions. So there's one theory that gives you many different models of quantum gravity. If you have something like a Swampland conjecture, which you believe is a general property of gravity, it should be true in all of this. So you can use, and this is what most people in the Swampland program do, and it's one of the most important things, you should use string theory as a theoretical laboratory. Okay? So the most important thing, if you come up with a new Swampland conjecture, it's good to have the other two, but the most important thing is to say, well, okay, I have checked this property in 1,000 string theory examples, and it's always true. To me, that is a hint that you're doing something right, because it's very little chance that you made a conjecture and you checked in 1,000 examples and it's all true in all of those. Well, things can happen. It's not perfect. Maybe all the examples that you're looking at are somehow a bit similar in some way, but this is the thing that in some sense is the most convincing. So that's how you go about Swampland. On one hand, general arguments, general proofs when you can. And another very important, you try to check against the theoretical lab that is string theory.
So correct me if I'm wrong, but if a particular low energy description can come from string theory, then it's not in the Swampland, right? Then it's in the landscape.
Yeah, that's the idea. So good. Sorry, I should have clarified that better. So string theory, we believe, is a consistent framework to obtaining quantum theories of gravity. So whatever you get from string theory, we believe is right. Okay? So you can use it to check.
Yeah,
if you
right.
get from string theory is good. If you get something that you think is in the Swampland, it better be the case that you cannot get it from string theory.
So, but does it mean that if you have a Swampland conjecture, and then there is some construction that comes from string theory, and for that particular construction this conjecture doesn't hold, would you throw the construction away or would you throw the conjecture away?
Well, that depends, right? It depends on the detail and the precision and the degree of control that the construction has, right? So, for instance, if I have some conjecture about, I don't know, like size of couplings, and I base this conjecture on a string theory example where maybe I take the ingredients of string theory, I take the fields of string theory, the couplings of string theory, but I haven't properly solved the Einstein's equations, which are the equations of motion of string theory, because string theory contains GR. Well, then in that case, very clearly, I would throw away the counterexample, because it's a counterexample that is just not really a solution, right? Of course, in practice, in the cases where it's not so clear, it's much more subtle than something as stupid as I said. Just wanted to illustrate the basic idea. But yeah, if, for instance, let me give you a concrete example of the other. Suppose you come up with the, I don't know. Suppose you come up with the.
Let me help you here. So there is one very famous, you can talk more about it, but there's a very famous Swampland conjecture called the weak gravity conjecture, which says that the gravity is the weakest force. And this is something that you have also worked on, where you showed that, DGKT doesn't go well with, weak gravity. So in that particular scenario, what would you do? Would you throw the weak gravity conjecture away, or would you throw the DGKT construction away?
Very good. So what I was going to say is that, for instance, if you come up with any conjecture that it's not true, let's say in n equals 4 super Mills or in ADS factors 5, which are completely well-established solutions with a lot of evidence behind of them, then you for sure throw away the conjecture. And the case you're talking about is something which is very, very interesting that we're thinking about right now. And the answer to that one is, I don't know. So just maybe perhaps to give a bit more context. So there is, as Hassan was saying, there's this one of the flagship Swampland conjectures, which is this weak gravity conjecture. Okay, tells you that in any consistent quantum theory of gravity, there has to be a particle whose charge to mass ratio, which is self-repulsive. Okay, so that its electromagnetic force is bigger than its gravitational force. That has a lot of evidence in string theory, and there's no string theory example, control or half under control, that challenges it. However, people have extended it to forces between, perhaps not just particles. Original formulation of gravity was about particles, but you can talk about forces between strings, forces between membranes. You could imagine like a membrane. And those ones, they are not in such a solid footing as the other ones. They are harder to check, but still they have been checked in many string theory examples, okay? In many string theory examples, they have been checked. And there's no black hole heuristic argument for them because the codimension of the membranes is very low. That's a technical point, but let's just know. And so in this project that you're mentioning that we had recently with Irene Valenzuela, what we were looking at was what happens to this conjecture. We were asking, is this weak gravity conjecture for membranes true in one particular scenario, which people have constructed in string theory, which is this called DGKT scenario. So this is a very interesting scenario because it's a vacuum, a string theory vacuum with negative cosmological constant, where the size of the extra dimensions is tiny compared to the cosmological constant. So that is the only example that we have like that. And that makes it very interesting because, you know, we don't see more than 4 dimensions in our own universe. So that vacuum is a lot more like our own universe than any other vacuum that people have studied in string theory with a negative cosmological constant. And it's very well controlled, but subtleties remain. So there's ongoing debates. I don't think the details are that important, but people are still debating whether this thing really exists, really works or not in string theory. And so what we wanted to do, the idea that we had was like, well, okay, let's see what happens with when we try to check this gravity for membranes, which is not super well established in this DGKT scenario, which is also well established, but it's not super well established. And what we found, as you were hinting at, is that the weak gravity conjecture doesn't hold in this scenario. So you are completely right. You either have to throw away the weak gravity for membranes, or you throw away the scenario. Now, let me tell you, this is a project which is absolutely great to give talks about because everybody's happy. Whoever likes the weak gravity conjecture tells you, oh, very good, the scenario doesn't work anymore, the DGKT scenario. And whoever likes the DGKT scenario tells you, oh, very good, you have proven the weak gravity conjecture doesn't hold. But the reality is we have done neither. We don't know. So we are actually now working to check weak gravity conjecture in scenarios similar to this DGKT, but which are under better control. They don't have this scale separation thingy, which makes DGKT very interesting, but in exchange, they're much better in control. So to answer your question, finally, I just don't know yet. I don't know which one I have to throw away. Do I have to throw away weak gravity or DGKT? But I know I have to throw away one of them, and either possibility is very, very interesting.
So for the DGKT scenario, I mean, so to construct the the vacuum that we call DGKT, we need these objects called the O planes, right? And the O planes, they have negative tension. And one of the approximations that people use is called the smearing approximation. So do you think that the result that you're getting is an artifact of the smearing approximation, or do you think that that's not the case?
No, it's not the case because we were not doing that. So the smearing approximation comes because, well, okay. So what's the smearing approximation? If there's any people listening to us which like myself cannot see without glasses, they will understand very easily what smearing is because that's what your eyes do when you take off your glasses. Okay. So what happens in string theory? We have this theory 10 dimensions, which we then compactify. And we can get an effective description where we sort of average everything that is happening in the internal space to get equations, effective equations that can capture the rough dynamics of the system and that are simple enough for us to understand in 4 dimensions. Okay, so that's what the smearing is. So it takes the orientifolds, but not just the orientifolds. Orientifolds, any D branes if you have them, and it's just like spreads them over the internal space like butter. That's just an approximation. In our paper, we were, so if you go to the original constructions of DGKT, even though they didn't prove rigorously, like at the mathematical level, they do have a picture of what things look like beyond the smearing approximation. So they have a picture like, okay, the orientifold is here, not there, it's not smeared. It's like this, is like that, and this is the one that we used, okay? There's also have been works justifying this picture order by order in perturbation theory. So starting from the smearing approximation in some perturbative scheme, getting better and better approximations. So that's why, like, when you go to the eye doctor and starts giving you lenses which are better and better and better until you find the right one. So people have been doing that. They haven't finished completely, I would say, But so far, everything they've done is consistent with the picture that, yeah, there's a concrete description of this thing in 10 dimensions, which contains no smear branes or oriented folds.
I see. So another thing about DGKT is that it has this parameter that which is called the Romans mass, which
Yes.
kind of inhibits it to have a strong coupling description, right? So do you think that's another reason why DGKT may be a flawed thing from the start?
Well, no, I don't think so. So I can tell you what I think about DGKT in a moment, but I don't think that the Romance mass really. We have other compactifications with Romance mass that we believe they're fine. Some of them have 16 supercharges.
Mm-hmm.
That means they are as well controlled as 8 factors as 5. Okay, so for instance, there's this background
Mm-hmm.
called type 1 prime string theory. Is one of the classical backgrounds of the second superstring revolution in the 90s. That one has Romance mass and orientifals, and people understand those very well. Now they are a bit different; they are less complicated than the ones that you have in DGKT, and people have discussed there might be some subtleties about what happens precisely at the core, close to orientifold planes that you were mentioning when there's
Mm-hmm.
Romance mass. And you can never know. There might be a pathology there, but at the same time, there's no obvious reason why things should be that bad. And we have other systems, for instance, which have O6 planes like the DGKT with Romance mass, and they seem fine. They seem fine. They seem to have holographic duals that, at first sight, they seem fine. Now, you could ask. So suppose that we establish. Suppose tomorrow a paper comes out in arXiv and says weak gravity conjecture for membranes is proven non-perturbatively. There's no doubt about it. What does that mean for DGKT? So I don't think it means that the solution that people found goes out the drain, that you need to say, okay, bye, doesn't work at all. Because all of these approximations, all of these checks that suggest that the thing is working, cannot go for nothing. Okay, so I really think that DGKT is a valid solution of 11-dimensional supergravity with some singularities. What I'm not so sure of is that it might be, because the thing about DGKT is a supersymmetric solution. I'm not sure. I think if someone tomorrow proves weak gravity is an exact statement, what I would conclude is that DGKT has some very subtle corrections that somehow break supersymmetry. So the vacuum is still there, and in some large N approximation is still perfectly fine, but maybe there's some little effect in the UV that breaks supersymmetry. And if it breaks supersymmetry, then it doesn't contradict anything we know, any expectation. The fact that it's scale separated, we already have other vacua which are scale separated without supersymmetry. So that would solve the puzzle, sort of. So it would be like, yeah, DGKT somehow exists, but it's not supersymmetric. In particular, that means probably that there's no holographic dual CFT. It means that the vacuum is non-perturbatively unstable, but otherwise it's fine, I would say.
So what you're saying is that DGKT may have some corrections such that if you add them to the DGKT vacuum, then the solution will be fine, right? If it happens.
What I think is that it might have some corrections such that the actual solution is non-supersymmetric.
Yes. Okay, I see.
But
Because
just to be clear, I'm not claiming that I think that's the case. That would be my take.
mhm.
If tomorrow somebody proves with gravity conjecture for membranes, with a bulletproof argument, it might
I
also
see.
be that with gravity conjecture for membranes is wrong.
Yeah, that can happen. So we have talked about the Swampland program, and we have, I think we have talked about the weak gravity conjecture to some extent. And you did mention the other one, the no global symmetries conjecture. Now, one thing about that conjecture is that it may seem as a very benign statement, but sometimes it can lead to, predictions of new kind of objects. So, for example, there was this paper. I think you were also an author of that paper, named Chronicles of Tubordia, where
Yes.
this thing was predicted that you have these R branes that came out of the necessity of the absence of global symmetries. So can you tell us about what these branes are and how do you get them just by requiring the absence of global symmetries?
Sure. So, it's very much the same discussion we just had for weak gravity. So for weak gravity, we were saying there's the weak gravity for particles. As I told you a little bit about it, and immediately went for weak gravity for extended objects because that one was more interesting somehow. And we spent, I don't know, 15 minutes talking about that. So with global symmetries, it's the same. You can talk about global symmetries like carried by particles like baryon number and such. And those are not the most interesting. Okay, so you can get some constraints, but as you were saying, they're very benign. They're easy to satisfy. But you can also imagine in some more complicated theories, constraints coming from symmetries under which the objects which are charged are extended. Okay, and it's when you demand absence of these additional global symmetries under which the charged objects are extended that you get all this extra mileage. Okay, so for instance, these the branes that we talked about in Duordia, we studied we discovered new branes in type 2B string theory using a technique which was pioneered by Kumkum Baffa and Jake McNamara, which is the use of a mathematical framework called cobordisms to find potential global symmetries of a theory, potential global symmetries under which extended are charged, and they're demanding that all those symmetries are broken because there are no global symmetries in quantum gravity. So what we did in that paper, we just sort of like turned the mathematical crank, and we found many, using this logic, we predicted many defects that were already known. For instance, we predict all known PQ7 branes that already people had discussed long ago in F theory, and that is very important because that gives you confidence in what you're doing. You're not doing nonsense. You're predicting what people know. So once we have predicted literally 10 objects that people know, and we get an 11th, and it's a new one, we take it very seriously. So we predicted this R7 brane, which is like the 7 branes of string theory. Only this one is non-supersymmetric. Okay, and it has exotic degrees of freedom living in its world volume. It has a massless 3-form gauge field in its world volume, which is something that hasn't happened in the world volume of a brane before. And it's quite interesting. And we gave evidence for its existence also using holography and so on. But there's many things that we don't know about the R7 brane still. So for instance, we're not sure what its tension is, and we are not sure it might be exploding or not.
So R is, stands for reflection, right? So
That's right.
why is it called a reflection brane? Is there a reason?
Yes, there's a reason. So this is a brane in type 2B string theory. Now, in type 2B string theory, there is this framework called F theory, where so the type 2B string theory has some sort of symmetry. This is an exact symmetry, it's a gauge symmetry. It's the kind of symmetry that's okay in quantum gravity. It's not a global symmetry. Which it's a certain group which is related to a torus, so like a donut. Okay, so if you are studying type 2B string theory, it really is helpful to imagine that at each point in space-time there is like a donut attached, and the symmetries of the theory have to do with the symmetries of this donut. Okay, so what are the symmetries of the donut? Well, if you picture a donut or a torus like a square, you can do things like rotating it, you can do things like slanting it, and essentially with those two you can generate many other symmetries. And it's just a mathematical auxiliary framework to understand compactifications of type 2B string theory, but this idea of a theory of thinking there's like this little torus everywhere has proven to be very fruitful. And for instance, the PQ7 branes of string theory, each of them are associated to one symmetry of the torus. So for instance, there's certain singularity which has to do with the fact that the torus does like this as you go around the singularity. Now, in all the transformations that people have discussed so far, the torus just does rotations or slantings. Nobody has asked what is the brane that you get when the torus flips like this or like that. So that's the transformation that it does on a reflection 7 brane. Okay. When I say not everybody, the R7 brane was predicted in some paper long ago, which is called Orientiful Precise, but it was like a one-line comment. And I think that's the only reference prior to our paper that suggested that something like that should exist. But anyway, so that's the thing. So that's reflections because it's reflecting the torus like this or the other way around, like that.
Sure.
And for instance, if you read our paper, you'll find there's two kinds of reflection 7 branes, and it has to do with the fact that there's two reflections on the torus.
I see. So, and just for the audience, I mean, when you're saying that, you can imagine a torus on each point of space-time, that's why, it's sometimes called said that F theory can be seen as 12 dimensional, right? Because you have this extra torus at each point,
That's
right?
exactly right. It's a very weird 12-dimensional theory, no? Because the moment I tell you a theory is 12-dimensional, you immediately think, okay, what happens if I move in the extra dimensions? But this in F theory, precisely because this torus is just an auxiliary device, you cannot move in the extra dimension. So it's like a 12-dimensional picture where you're constrained to live in a 10-dimensional slice of it. But yeah, that's exactly why people say that the theory is 12-dimensional.
So, one thing that I want to ask you is that, so we have these, swampland conjectures. There are many of them. We have talked about some of them. Have people looked into the relationships between these conjectures? And if they have looked into the relationships, then what kind of relationships have they found? Are they
Good. So
independent conjectures? That's what I want to ask.
for the most part, they're not independent conjectures. People have looked at the philosophical level. I don't think there's a single one which you could think of as independent of the others. So people have looked for and found really all sorts of relationships between the conjectures. Okay, and even try to find what is the fundamental conjecture. Is there a fundamental conjecture that gets all of the others? So there's three conjectures which are very strongly interrelated, which are the no global symmetries conjecture, the weak gravity conjecture, and the distance conjecture. So the distance conjecture, what it tells you is okay. So the distance conjecture is a statement about what happens in string theory when you take some parameter of the theory and you make it very large or very small. So what do I mean by a parameter? So in string theory, as the people listening to us might know, it's actually a 10-dimensional framework. It's a 10-dimensional theory. So you often compactify on some internal manifold to, let's say, 4, 5, or some lower dimensional theory. And well, the moment you do that, it's very obvious to say, okay, what is the volume of the manifold? What is its shape? And so those are the parameters I'm talking about. They are expectation values of fields in the lower dimensional theory. They're called the moduli. And so you can ask, okay, is there any universal behavior in string theory whenever the volume becomes very large or a space becomes stretched very much or something like, whenever you should imagine of a compactification as a laboratory with some knobs which control the size and shape of the manifold. So of course you ask, if you're like me, when you have like a control thing, you say, okay, what happens when I turn it to the maximum or to the minimum? That's what you do. And so what the distance conjecture tells you is that whenever you take any of the knobs and send it to infinity, a universal behavior happens, which is that there's a tower of states, of massive states, which are becoming light very fast, exponentially fast, and they're destroying the effective field theory. And so this is related to all the other conjectures, because you might ask, well, why do I have weak gravity particles? Well, there's this paper by Omori, Cordova, and Rodilius, where they argued that you must have weak gravity particles if there is a global symmetry for Wilson lines, so for a particular kind of one-form symmetry. If you demand that it's broken, strongly broken, and at or below the Planck scale, you get the weak gravity conjecture. And you don't get just one particle. You just don't get one weak gravity particle. You get a whole tower of them. What is this tower? The tower of the distance conjecture. You can check that this tower behaves with respect to the knobs that I was telling you before in exactly the way to get you the distance conjecture. So that's a connection between the three of them. It's often the case that the tower of states that satisfies weak gravity is the tower of states that satisfies distance conjecture.
So the distance conjecture thing that doesn't tell you where the tower comes from. It just tells you that there needs to be one, right?
That's correct. That is correct. In practice, there's so that's the distance conjecture just tells you that. But then, of course, you can go and ask what happens in practice. Okay, and so there's a slight strengthening of the distance conjecture, which is called the emergent string conjecture by Lee, Lerch, and Weigand from 2019, which is very nice. They observed that, okay, fine. So there's infinite towers of states. What is the nature of the tower? And they go example by example by example, painstaking. They check lots of examples, and what they find is that in every single case, the nature of the tower is that it's either like a perturbative, the oscillation modes of a string which is becoming light, like in perturbative string theory, or the compactification manifold. So it's some manifold which is becoming very large, and then the Kaluza-Klein modes of that manifold are becoming very light. Kaluza-Klein modes are like Fourier modes. If the space is very large, the modes become very light.
Right. So if a tower of states become light, it means that the effective field theory description breaks down, right?
Yes. So to be more precise, if you are an observer that if you are interested only in exactly phenomena of exactly massless energies, that zero energy, then okay, you can ignore it. But suppose you're a reasonable observer that is interested in anything that happens at any finite energy scale, because this tower of states becomes exponentially light, exponentially quickly, okay, as you change the value of this knob, pretty soon the tower is gonna enter the energy scale, is gonna get at or below the energy scale that you're interested in. Let's say they were interested in energies like LHC, energies like 1 TeV, then or a few TeV. And then as I increase this knob, at some point, this tower is going to get very, very light, and I'm going to start seeing them at LHC. So the effective field theory that I had originally, which didn't include this tower of states, is breaking down.
Right.
And
So, but don't you think that this is a conjecture that is giving you an implication that you could have anticipated from the start? You would know that in quantum gravity, the effective field theory description will break down somewhere. So do you think that this is like an expected thing, at least?
well, I guess what you're saying, I'm not sure exactly what you're referring to, but I guess what you're saying is that if you imagine any theory of gravity coupled to, let's say, a scalar field, which is like this knob, if you write a general action for this thing, right? You would expect to have Planck suppress operators. They will appear somewhere, and then effectively will break down somewhere. That is true. The important thing of the distance conjecture is that it tells you how fast the tower of states should become light in examples. Okay, so you cannot just push that way. So the question you can do at two levels. So there's a quantitative question of when the tower becomes light, and it happens to become light in just order one or a few M Plancks. So that puts a quantitative bound on how far out you can get, which the general heuristic argument wouldn't give you. And even if you wouldn't care so much about the quantitative things, you're interested in the point of principle thing, it's true that you would expect perhaps the effective theory to break down, but that's not a proof. You could ask, okay, what is wrong with just having an exactly massless scalar field with some symmetry that protects it and prevents the thing from
breaking down,
and the thing from breaking down.
Yes.
So that's another interesting.
So distance conjecture is telling you that the breakdown of effective field theory happens much before you would have thought naively, right?
Yes.
Right. So when you were describing distance conjecture, you said that if you go to a large distance in the moduli space, right? But the thing
Yes.
is that in order to use the word distance, you need to put a metric on the moduli space. So what metric do you put? Is there a
Very
unique
good. Very
metric?
good. No, well, okay. So there is a canonical. There's in any effective theory coupled to gravity with scalar fields, which are like the values of these knobs. There is a canonical metric that you can use. And if you think about this is a bit more technical, but the way we describe these fields is by having a Lagrangian, right? So you have an effective field theory, and if you have scalar fields and there's a Lagrangian on the scalar fields, there's a kinetic term. No? So what does the kinetic term look like? If you have several scalars, it looks like a symmetric matrix. It's symmetric and it's positive definite, and it's because the kinetic term should be positive because of unitarity. Going back to what we were saying at the beginning, and it's symmetric, positive, definite. It's a function of moduli space. It's a canonical metric in moduli space. So that's the one used. It's the metric of coming from the kinetic terms when written in Planckian. So it's very, very natural. Of course, you could come and say, no, I don't like this. I have my personal metric, the Hassan metric, which is exactly the metric you were using multiplied by 3. And you're, of course, welcome to use that. But remember to divide all the expressions that people wrote in the literature by 3.
Sure. Okay, I see. So one more thing is that there is a very quite well-known prediction from the from the Swampland program. I think you have mentioned it somewhere else as well, and that particular prediction has to do with a particular theory called super Yang-Mills theory, right? SUN super Yang-Mills, and the thing is that if correct me if I'm wrong, that if n in n SUN is 22 or less, then it's fine, but if it is more than 22, then it goes to the swampland, right? So can you tell us a bit about that prediction, and can you tell us that what goes wrong if n goes higher than 22?
Yes. So let me first qualify it, because that's very important. So the bound you're talking about is a bound about coupling n equals 4 super Yang-Mills to gravity in a supersymmetric way, preserving all 16 supercharges. Okay, so that's a bound on theories with 16 supercharges.
Mm-hmm.
If, for instance, you want to put n equals 4 coupled to a gravitational sector which has n equals 2 or n equals 0 or whatever, you can go beyond the bound. So let me get that clear. Okay, so this is a bound about coupling n equals 4 super Yang-Mills field theory to gravity in a way that preserves all supersymmetry. Okay, so that makes it a much more stringing question. Okay, so that's the statement. Now, what goes wrong if you try to put n bigger than 23? So this is a paper. This bound comes from a paper by Hichol Kim, Huri Tarasi, and Kunrum Bafa, which is called n equals 4 and the Swampland. And so what they argue is that if you go beyond that limit, you are going to get a violation of the distance conjecture. Okay, so you're going to get so you could take a theory which has any SU50, for instance, you put on a circle, and then you take an infinite distance limit when the circle becomes very, very small, and the resulting theory in the limit violates a version of the Swampland distance conjecture. It has too many high-speed modes. Now, you can then ask a more precise question. You say, okay, fine, I buy the Swampland argument, or I don't. I want to understand why is this not possible in perturbative string theory. You can ask, how does this bound come about in perturbative string theory? And in perturbative string theory, for instance, heterotic strings just comes from the fact that the Worship central charges of heterotic strings do not allow for current algebras, which is how you would describe the gauge symmetry, with more than 20 with 23 or more, right?
Mm-hmm.
Now and then you can ask, okay, fine, how can I see that from the point of view of D-branes? So that's another corner of the modalized space. And in the other corner of the modalized space, what happens is that the number of vectors you can have is the number of D-branes you can put in the compactification. And with n equals 4 supersymmetry, there's just very few compactifications. There's just essentially one. There's a few more, but the biggest that you can do, there's a few of them, less than 20. And so you can find how many D-branes can you put in each of them while making sure the total charge vanishes, because the D-branes are in a compact space. And the most you can put is that. So that's another one.
I see. So another question that I have is about the nature. So, okay, for example, there is this very famous thing that a lot of people say. For example, if you look at the string coupling constant, right? It's e to the power of phi, which is phi is known as a dilaton. And when people who criticize string theory, they say that you have a parameter. People say that no, this is actually not a parameter. This is more like the vacuum expectation value of this dilaton, right? Probably you have seen this recent paper by Thomas Banks, where he was arguing that that's not the case. So what is your take on that? Should we call this a parameter or not?
So that paper. So let me see if I remember. First of all, there is a very nice reply by Ashok Sen, I think.
Yes, I saw that.
So I subscribe everything that he says. So what Tom Banks is saying, if I remember correctly, I mean, this was in February, but he's been saying this for a long time, but I kind of like, if I'm not...
I think he was saying that these things are values of the field at the infinity, therefore they can be seen as super selection sectors, things like that. But he was saying that you should not refer to the string coupling as not a parameter. It is a parameter actually.
Well, the vacuum expectation. Yeah, I think I remember he was saying something about the energies. Anyway, so I think that, for instance, ADS factors is 5. So he was making this point mostly about ADS spaces, right? And I think the point is that different values of the. So if you imagine you have, for instance, to be concrete, ADS factors is 5 with different values of the dilaton field. Okay, those are dual to different conformal field theories. Okay, so I think in that sense, he's thinking about them as different physical theories. But these different physical theories, they're all part of this one parameter family of deformations. And the only reason why they look different is because the CFT is sort of at the infinite boundary, so it takes infinite energy to deform one into the other. Okay, but if you're in ADS factors as 5 with value of the dilaton, let's say 1, and you want to construct, you can construct a big bubble where the value of the dilaton takes any other value, SN equals 2, and that costs finite energy. Okay, so that's what it means operationally. You can discuss, because I remember vaguely when I was reading the paper to think that the thing was, of course, what Thomas was saying was in some sense not wrong, but the definition that he had for what a modulus is versus what it's not, he was claiming a lot more than one would claim intuitively. For me, if you're able to, if you have someone tells you that the theory of the world has some parameter, let's say the fine structure constant, and I have a procedure by which I can engineer in a lab a different value of that constant, so it's different where you are from where I am, that is a field, that is something that can fluctuate in space. And all fields of string theory, the dilaton and any other field is certainly like that. It may cost energy, but you can change its value in a finite region. So that's what it means that it's the web of a fluctuating field.
I see. Okay. Another thing that I want to ask you is something that you have also worked on, and people who worked on this work on the Swampland program, they have worked on that particular idea a lot in the last like 3 years, I think, and that's the concept of dark dimension.
Yes.
And using that concept, correct me if I'm wrong, some people are also speculating relationships between dark matter and dark energy, and they think that probably they have a same source or some kind of that, something like that. So can you tell us a bit about that particular idea? What is that idea, and how does it relate
Yeah.
to dark energy and dark matter?
Yeah. So dark dimension is essentially it's an idea you can motivate by taking the distance conjecture very, very seriously. And so you take distance conjecture very seriously. So you think you just assume it's true in every possible infinite distance limit of string theory. And 2, you ask or you postulate that our own universe is close enough to one of the asymptotic regions of string theory. And 3, you combine the first 2 with experimental data. Okay, so that's the idea of dark dimension. So the basic observation behind dark dimension is you go to string theory, and then you look at infinite distance limits where there is a vacuum energy. So you can look at many limits which are supersymmetric. Okay, but you can also look at limits which are non-supersymmetric, where there is a dynamical vacuum energy which is generated by the compactification by fluxes or quantum effects or whatever. And you can ask, is there any relationship at all between the value of the vacuum energy and the mass scale of the tower? Remember, we're at an infinite distance limit, so distance conjecture is telling us that the tower is getting light. Is there any general relationship between the size, the mass scale of this tower and the vacuum energy? And it turns out the answer is yes. Okay, and the relationship is that the vacuum energy, in all examples in string theory, is like the size of the tower to the fourth, in 4 dimensions, size of the tower to 4th power or less. And with that, you go and check with experimental data. Okay, because so for instance, one thing you can rule out pretty quickly is that there is a very light string, because we have seen that in LHC already if you take that scaling into account. So the bottom line is that you relate the vacuum energy to the size of the tower, and the only possibility that remains is to have the tower be decompactification. Sorry about that. To be a decompactification, okay, and that this decompactification is of exactly one extra dimension, and you can even estimate its size. Its size is around between 1 and 10 micrometers. Okay, you get that estimate if you just say, well, let's say that we have one extra dimension decompactifying, and let's say that the Casimir energy of that extra dimension is comparable to the total value of the vacuum energy, then you get that estimate of between 1 and 10 micrometers. So that's a very exciting scenario because that's not so far away from the region of that is being probed by searches of extra dimensions. And in fact, there is a group of Marcus Aspelmeyer in Vienna where they are doing an experiment to measure deviations of Newton's law, which is something that is sensitive to the presence of extra dimensions. And they're doing that to check. They're hoping to get to maybe around 10 micrometers, hopefully. So that's very, very exciting. There's, as you were also mentioning, there's people that have connected, with myself included. You have connected it to also to dark matter, because the moment you have one concrete scenario, and dark dimension is one such scenario, it is natural to try and, well, this is the right thing to do, to try to do model building and see if you can explain other things. So, for instance, can you explain the abundance of dark matter? And so, with a few more phenomenological assumptions, you can relate the two of them. So, for instance, in this a natural scenario is that in dark dimension, the dark energy is just the Casimir energy of this extra dimension, and the dark matter is the mass of KK gravitons living in the bulk of the extra dimension. There's another proposal where the dark matter is, for instance, given by 5-dimensional black holes. Both similar.
I see. So I would ask you to address one criticism that some people have. For example, I think almost 10 months ago, I had Fernando Quevedo on the podcast, and he said that he finds the idea of dark dimension to be just a reincarnation of the ideas that like Nima Hamed had in the late 90s, because they were also talking about a millimeter level dimension. So do you think that that's different, or do you think that it has some overlap?
No, it has similarities, but it's a different idea. It's first of all, the scenario that Fernando was talking about is about two large extra dimensions. Why two, and why do we get one? Well, the thing is, what Nima and friends were trying to do. So there was Nima Hamed, Guia de Valle, and Dimopoulos as the original large extra dimension paper.
Yes.
What they were trying to do, they were trying to connect the size of the extra dimensions to the Higgs mass. So they're trying to solve what is called the electroweak hierarchy problem. Why is the mass of the Higgs, or the electroweak scale, so much below Planck mass? Well, it turns out that with two extra dimensions, the electroweak energy scale comes about at the higher dimensional Planck mass, the real scale that controls gravitational dynamics of the theory, appears at around TeV, or a few TeV. So what that means is that the hierarchy between the Higgs mass and the fundamental scale is a factor of 10, which we are happy with. Maybe in the fundamental theory comes of a calculation which is like 1/2 pi or something like that. Okay. In the dark dimension, we are also trying to use extra dimensions to explain a hierarchy, but the hierarchy is different. What we're trying to explain is the cosmological hierarchy. Why is the cosmological constant so small? Okay. So with one extra dimension, you relate the vacuum energy like MKK to the 1/4, and so you can relate the vacuum energy to the size of the extra dimensions. But just to illustrate the difference, the Planck scale, the fundamental scale of gravity of the 5-dimensional gravity theory in dark dimension, is at 10 to the 10 GeV. So it's much higher. So if we are right, we are not going to observe that in the collider. Okay, we might observe some effects, but certainly not directly that. Okay.
I see. Yeah, that makes sense.
That's the basic difference, I would say.
So you're saying that with the collider energies that we have available today, it's not simple to probe the energies that you're talking about, right?
Well, not not directly probe the gravitational energies of the extra dimensions. So okay. So Planck scale in 4 dimensions. If imagine the universe was just 4-dimensional, so everybody's wrong. There's no large extra dimensions, no dark dimension. Then the fundamental scale is probably around the Planck scale, which is 10 to the 19 GeV. Okay, so the scales that we are measuring today with colliders are 10 to the 3 GeV, so 16 orders of magnitude away. Now, suppose there's one extra dimension, like in that dimension. Then that brings down the fundamental scale of gravity from 10 to the 19 to 10 to the 10. So it's 10 orders of magnitude lower, but it's still a factor of 1,000,000 or 10 million away from what we can measure today. So we're not
Right.
going to measure anytime soon directly. There are papers, for instance, there's a nice paper by Feng-Yun Xu, Timo Weigand, and Gonggun Bafa, where by adding additional assumptions, which are, I think reasonable, but they are nonetheless additional assumptions over the bare bones third dimension scenario, you can get predictions that suggest that maybe you will observe things at LHC or close to it. But yeah.
I see. I see. So, um, let me change topics a bit. I mean, just a bit, not a lot, because they are still related to what we're talking about right now. So, since you also work on string theory, string compactifications, there has been a lot of interest in the last few years regarding scale separation, right? We were talking about scale separation just a minute ago.
Yeah.
Why do you think that the examples with scale separation are so rare? That's one question. And another question is that do you think that we will find more scale separated examples in the future?
Okay. So to the first question, why are they so rare? It has to do. It has to do with the fact that the discussion of scale separation is typically about ADS examples,
Mm-hmm.
and the solutions that we like to get, because they're the ones that we control the best, are solutions which have supersymmetry. Okay, so when you have supersymmetry in a theory of gravity in ADS space, it is very often the case that you get what is called a gauge supergravity. You get gauge fields. Okay, so for instance, in ADS factors S5, you get gauge fields under gauge group SO6, which have to do with isometries of the internal space. And just from supersymmetry, from the superconformal algebra, you can show that you're going to get some gauge fields in ADS5. Okay. Now, the thing about these gauge fields is that they remember there's weak gravity conjecture. So if you have gauge fields, you have towers of light charged particles. And if you look at what weak gravity imposes, is whenever you have these gauge fields, which are always there the one you have extended supersymmetry and even minimal supersymmetry in dimensions 5 and above, these tower of states that have to do with gravity related to these gauge fields are going to be such that they will look like the Kaluza-Klein states of an extra dimension. So just from supersymmetry and with gravity, we are going to essentially in any superconformal algebra which has an R symmetry, okay, we are gonna get weak gravity states, and we're gonna get not a scale separated, not scale separated solution. So if we want to get scale separated solutions, we need to look at minimal supersymmetry. DGKT is 4D equals 1. Okay, there's no symmetry there, so you can get scale separation. But that's why we're discussing about it. It has so little supersymmetry and it's difficult to control. And that brings me to the second question: are there going to be more solutions? Well, there are already some. So there was this solution that we were discussing briefly before the podcast, which is like a T-dual version of DGKT, which is like an M-theory compactification, which in principle is scale separated. There's a bunch of solutions in 3 dimensions, and I think that people are building some more examples as we speak. So there will for sure, there are more solutions, there will be even more, but they all have the same kind of features, that because they have so little supersymmetry, which is a necessity to have even scale separation in principle, they are not super, there's always questions about them, about back reaction of orientifals, the kind of questions that we were talking about before.
So you said that you will get a tower of light states, and this tower is the tower of KK modes. Well, if this particular tower was a tower of winding modes, that would mean that the dimensions are small. So do you ever get a tower of winding modes instead?
Mm, in some sense, in some limits, but in anything that is well controlled by supergravity, the answer is no. So okay, so what sets the size of the scale is the gauge coupling of the gauge field in Planck units. Now, if we are talking about a theory with extended supersymmetry, and we're talking about the gauge fields which are part of the gravity multiplet, The gauge coupling of those guys is controlled by G Newton. It's controlled by gravitational Newton's constant. So it's fixed, okay?
I see.
And when you do the calculation, it comes out to be like ADS scale mass gap.
I see. So does it mean that, the number of theories, that come from, string theory that do couple to gravity, which are in the landscape, they are small, but the set of theories that have scale separation is even smaller. Actually, it's actually very, very small. So do you think that that actually tells you that the framework of string theory is even more constraining than some people think, when it comes to describing?
Sorry, because there's something to upset. The discussion that we do about scale separation, and the reason why scale separation is interesting, is about supersymmetric examples.
Yes.
Because if you have a supersymmetric example which is scale separated, that would give rise via the ADS CFT correspondence to CFTs with very weird properties. And because we would like to have models like that to do things like uplifts to the sitter, like a guilty and stuff.
Sure.
If you don't care about either of those things, there are many, many examples of ADS solutions which are scale separated. Okay,
that's true.
So, for instance, there's a solution by it's in a paper by, I don't remember all the authors. It's a paper on optimal transport. It's Alessandro Tomasiello and Bruno De Luca, and there's I think another author which I'm forgetting. I'm sorry about that. So in that paper, for instance, it's a paper about something else. But if you go to the appendix, you will find an ADS. I think it's ADS 4 cross T7 compactification of M theory with fluxes and Casimir energies, which is an ADS compactification, and it is scale separated. It's completely scale separated. Okay, so that's very interesting because it uses an ingredient which is intrinsically non-supersymmetric. That's Casimir energies, and it shows that the moment that you allow yourself to do that, scale separation is just right there. The construction of it, what they do using a torus is very nice because it allows for a lot of control. It's in some sense like the simplest space, but it will work with many, many other spaces. So what that tells you is that there's probably a large landscape of ADS solutions which are scale separated like that. They're not supersymmetric, but scale separated. They probably don't have a holographic CFT because the moment you have something non supersymmetric, there is typically instabilities like bubbles of nothing, which prevent the existence of a holographic dual CFT. But they're there as an ADS solution. That's completely fine. And furthermore, we also have examples of supersymmetric scale-separated solutions if you have Minkowski space. Type 2B or type 2A, type 2 strings or heterotic on any Calabi-Yau manifold gives you a Minkowski solution, 14 equals 2, and that is automatically scale-separated. Because scale separation is defined as the ratio between the KK scale and the curvature scale, and the curvature scale is 0 for Minkowski.
That's true. I think I'm missing something. So when you said that you compactify M theory on T7 and you get ADS4 cross T7, did you also say that that particular thing is non-supersymmetric? How can that be non-supersymmetric?
Let me explain. So, well, first of all, if you try to so compactification on T7 is supersymmetric. That's if you introduce no fluxes, you need to introduce a flux, so that breaks supersymmetry.
Oh, okay.
But on top of that, what they do in that paper is they actually take a torus, a T7, and they impose non-trivial boundary conditions on the fermions, such that along any one cycle of the torus, the fermions become antiperiodic. Okay, so that's what people sometimes call the twisted torus, spin structure. No, it's not twisted torus. It's something else. It's called twisted spin structure or non-trivial spin structure. So what that means is that fermions become antiperiodic, and that alone breaks supersymmetry and is responsible for the existence of the Casimir energy.
Did you say that they introduced the boundary conditions on the fermions or on the torus?
So it's a boundary condition on what does the fermion do as it goes along the torus. Okay.
Sure.
So usually on a torus you will impose periodic boundary conditions. So if your fermion is psi, for supersymmetry you would typically say psi of x plus 2 pi is equal to psi of x. What they do is psi of x plus 2 pi equals to minus psi of x.
Right. So that's why it's twisted spin structure. Okay.
That's exactly right.
I see. So people also have discussions regarding scale separation when it comes to CFT, right? So do you think that we can have a particular thing to look for in CFTs? For example, if you have a big gap of something called the conformal weights, and if you can find that CFTs like that, then we can find scenarios where you have scale separation. You're using some holographic prescription.
Yeah, in some sense, scale-separated scenarios are like a supersymmetric analog of, or a small extension of pure Einstein scenario. So one thing that people look for is the hollow, and in some sense, using wormholes, and so they have found averages which a bit look like that. They are like the holographic dual of pure gravity, just gravity and nothing else. So in a scenario like DGKT, what you have is gravity and a bunch of scalars which are more or less light, and then nothing else. Okay. So, to the extent that you can ask, people have tried to answer these questions using CFT techniques, you could ask the same about DGKT. There are versions of scale-separated scenarios which are in 3 dimensions. So there are ADS3 CFT2 in principle, and those are a lot more interesting for that because in CFT2 you have a lot more power. The conformal group is larger, there's modular invariance. You might be able to use some of that to constrain those models in a way that you couldn't in higher dimensions. But since you ask about the CFT, let me tell you something very, very interesting that happens for scale-separated scenarios, which is quite funny, which is the mystery of the integer conformal dimensions. So I'll take DGKT, just the vanilla DGKT. Effective field theory is Einstein, as we were saying, Einstein's gravity plus a bunch of scalars. The scalars have some masses. The masses are of order the ADS scale.
Mm-hmm.
Compute the masses, and the masses come out to be integer numbers in ADS units. So it's like 11 or whatever over the ADS landscape. Fine, that's maybe curious, but you're not so surprised. After all, this comes from string compactification, where a lot of things are quantized. Maybe it's not so weird that the numbers are integers.
Mm-hmm.
However, then you ask, okay, what do these massive scalars with masses of order, which integer masses in ADS scales correspond to in the dual field theory? And then there's a formula that relates masses in the bulk to the dimension of the dual operator in the dual field theory, which is mass squared equals delta, conformal dimensions, times delta minus 4 in 4 dimensions.
Yeah.
That's a quadratic equation. If I give you a quadratic equation with integer coefficients, still the solutions are irrational. For instance, x squared minus 2 has irrational solutions even though the coefficients are integer.
Yep.
However, it turns out that the masses of the scalars are such that the dual dimensions that come out as solutions of these quadratic equations, they also are integers. That's very surprising. Okay?
Mm-hmm.
Why, why does this happen? If you have an n equals 2 theory, you could argue maybe there's like conformal, superconformal R symmetry, and there's some operators of the unitarity bound. You can argue their dimensions are integers, but here's a 14 equals 1 setup, so there's no such thing. So at least, of course, these dimensions, they get corrected by finite n effects, but in the infinite n limit, they are integers. And
Yes.
so far, I don't think there's a very clear explanation for that.
Oh, okay. That makes me that gives me a bit of solace because I saw some papers in the last few months. I think one paper was by Vincent Van Hamlik, and there was another paper by I think Gribori, I think, and they were talking about this integer conformal dimensions, and I couldn't realize that why that's a big deal. But now you think that we don't know why why that's the case, right?
We don't know why that happens because there's, sometimes the only reason for interior conformal dimensions is when they're protected by some sort of symmetry.
Mm-hmm.
So it could be like there's some sort of Galilean symmetries that can protect them, but it doesn't seem to be at play here. It could be something like an R symmetry that emerges at infinite n, but I think that's something like that, but nobody has made that precise.
Okay, so I think my technical questions are almost over. I need to ask some other questions before we can wrap this up. So before we, go to some other questions that I want to ask later, can you tell us how did you get interested into physics, and what got you into studying theoretical physics?
Well, so I think I don't. I just since I was a kid, I think I was generally interested in understanding how things work, and I always like to understand things at the fundamental level. I feel like I really want to understand why the universe is like it is. I know it's like a vanilla answer, but it's the true answer. So since I was, relatively young, I wanted to pursue a career on theoretical physics. I thought it was something very, very cool. Um, there's this thing, when you grow up as a science enthusiast, right? Is like it seems like the coolest thing to do, and it would be so awesome to be able to contribute to that. But everybody seems so smart, it's Einstein, Newton, all the people who did all these things. So can you really contribute something? And so one message that perhaps I would like to say is that, so this is something that, for many years I had this kind of questions, and everybody has them, or mostly everybody have these questions about, well, can you really contribute something, or are you good enough? Are there these
Yes.
can you contribute something meaningful, or is it just impossible? And one thing that I'm very happy to say is that I learned over time is that I think that image, like the image that science is done by a few geniuses, is wrong. If it was true in the past, in the 19th century and 18th, I think that's because, generically speaking, science was done. If it seems like only 10 people did science, was because there was probably 10 people worldwide doing science anyway. Because, in the 18th century, there was famines, war, it was
Yes.
19th century. So there were not that many people doing science. So one really beautiful thing that I think one discovers when one goes through the academic career is that it's really a very collaborative thing. And everybody can contribute, I think, really quite meaningful stuff, as long as you keep thinking about the big problems and are willing to work.
Right. So, was there, a book that you read when you were young that got you into physics, or no? I think you were just interested in physics from the very start.
Well, I mean, for sure there were some. Maybe not a book that is just like.
Mm-hmm.
Well, there's a book by, I think it's Peter Atkins, which is called Galileo's Finger, which is just like it's just
Yes.
like a short book which tells you like different things about different sciences. Like, for instance, one of the things it describes is how Eratosthenes measured the circumference of the Earth. And I remember reading that and thinking, wow, that's so cool.
I see.
Um,
So,
that-
so you just mentioned that people tend to think that science is done by geniuses, right? Uh, but one thing that a lot of people don't realize is that a lot of people that do very very good in theoretical physics, they do a lot of hard work. So hard work is really really important.
yeah,
When it comes to contributing. For example, even in our times, we have someone like Edward Witten, and people always say, "Oh, he's such a genius." A lot of people don't realize that he's a very hard worker, right?
yeah, yeah.
Right. So, what do you think about the importance of hard work as compared to just being a genius, right?
I think that was absolutely essential. And the moment, for instance, for me, when I sort of like realized, became convinced of what you were just saying, that it's really a lot more about hard work than about smarts, I became, very happy, because all these questions about can I contribute, they just became, yes, I just need to work very, very hard, right? Or need to work
Mhm.
hard. It's not like you should do whatever you like, but it's also not necessary to just push everything else in your life aside or anything like that. But you do need to work hard, and if it's something that you find interesting, um, that's why you should always try to work on things that you find interesting. Then it's not so hard to work hard.
Right.
And indeed, cases like Ed Witten, I'm sure you just, no matter how smart you are, you just look at this at the amount of stuff he produces. Even now that he's I think he's around 70 years old.
Mhm.
Uh, he's clearly someone who's absolutely passionate, and that is
Yes.
absolutely key.
Right. But do you think that another thing that is very important, and a lot of people struggle with this, is that if you want to produce something, meaningful to the the knowledge that we have about theoretical physics, you should also be prepared to fail again and again. A lot of people get bogged down when they fail, right?
Yeah,
So what do you
that,
think
that
about that?
that's particularly true, because oftentimes, like, people who get in high energy theory or string theory or quantum gravity, they tend to be good students. So a good
Mhm.
student is someone who is used to the following situation. You have some challenge, which is the course material. You study the challenge. It may take more or less effort, but it's a finite amount of effort. Once you do this, you completely dominate the thing, and then you go to the exam, you get good grades, and you continue. Okay? Research is not like that. It's completely not like that. And so people who come from that background, they oftentimes have a hard time because they have not had to struggle, at least academically. But the point about research, is the way you make a lot of progress is, you need to try a lot of things, and a lot of them will fail, and then you try the next thing. And the fact that you fail doesn't mean you're done. It means that you try something and it fails, so you need to keep trying. And if you keep trying, not only with each try, even if you fail to do whatever you wanted to do, you get better and better and better, even if you don't realize it. And eventually what will happen, for instance, if you're a PhD student, is you start doing things on your own, and at some point you have a very cool idea, and it was done by someone in the 60s. It's like, okay, that's good. You're in the good track. You're just a bit late. And then you keep working, you keep thinking, and eventually you'll get something which is a good idea that you can work on, and it will work out. But it's all the time like that. And the thing is, one needs to learn to enjoy that process, which is fun in itself. It's like you think about something, seems curious, and the thing, if you care more about understanding what is going on in the problem at hand rather than whether it's going to be important or not, then you're going to enjoy the process a lot more, and the chances that you end up doing something maybe important are higher. But the more important thing is whether you do something important or not, you at least enjoy the process. Okay.
So this transition that you talked about, the transition that a student has from, taking exams to doing research, there is one more aspect about this transition. And I think I also talked about that in my previous podcast. The, the problem is this. So when you're an undergrad, for example, right, and you are solving a problem from your book or, from a problem set, suppose that you're not able to solve that problem. You may take a day or two and you're still not able to solve that problem. Now,
Yeah.
a lot of people in this particular scenario will think that, okay, probably I'm doing some mistake here. This problem is solvable. Otherwise, it would not be here. It would not be in my problem set, right? But then you go to grad school, okay, the problems may take longer. They may take weeks, right? But you still know that this is solvable, and I will be able to solve it in like probably at most a month, probably. But in research, you never know. The problem may
Yeah.
be, it may be probably unsolvable for like one more century. You don't know about that, right? So
But
how does one deal with that when you go from being a student to being a researcher?
like, it's like any other, really, like anything in academia is really no different from any other thing in the world. Just things sometimes take more practice than others. So the skill to realize when to continue working on something, when to give up, and more importantly, when to think, okay, what I did is not exactly what I wanted to do, but what is it good for? Can I
Mm-hmm.
turn to that? So it's something that one learns with experience, okay, by doing more and more and more, and that's just it. But it's very it's important to keep that resilience, and to understand that that's just it might have a solution, it might not. If you try for a while and it does seems like it doesn't have a solution, ask yourself, try to get it's very important to get physical intuition, very, very important. If you're trying to solve something that doesn't have a solution, you say, okay, why, what is the exact reason why this is not working? Try to get a physical picture. So that really helps a lot with deciding what to do. And oftentimes, even if what you want to do exactly doesn't work, there's something close related that you can do and it does work. Or the failure is telling you something which is even more interesting, perhaps, they were interested originally. And this distinction that you were saying between problems that have solution and problems that don't, and how the first ones are the ones for undergrads and the others are for research, is really a distinction of time. I still have, I think, it's stuck in my mind. I remember I was many years ago studying like some condensed matter course, and there was a problem in a book. Unfortunately, I don't remember the book, but there was this problem in this book, which was some problem. It was not terribly difficult. Okay, it was not the easiest problem in the book. It was not the hardest, and it had a footnote which said, if you had solved this problem in 1967, congratulations, you could have published a PRL. Okay? And that's the entire difference. The calculation is not hard.
Yes.
The entire difference is what you were saying. In 1967, nobody knew this was an interesting calculation with a solution. And afterwards, people thought, oh, that's cute. I'm going to put it as a problem in my book.
Yes. I mean, that reminds me of a quote, but I think that quote takes things a bit further. But that quote is from Richard Feynman, so probably Feynman can say it. He said that there are two kinds of problems: easy problems and unsolved problems. And probably that's true to some extent.
There's another quote which is related, which I really like. I don't know who the quote is from. I just read it somewhere and it stuck, which is like, science is any endeavor in which the average people in one generation can get farther than the geniuses of the previous one.
That's true. Yeah, because they are standing on the shoulders of giants. That's why. Yeah, I mean, the example that you gave, I think there was another example. For example, I read this book um, on elliptic curves, right? And the last chapter of that curve of that book was about the Fermat's last theorem, and I was like, this is a problem that have kept people, occupied for like 350 years, and now this is just a chapter in a book,
Yeah.
right? So, right. So yeah, what you're saying is incredibly true. Okay, so one more thing that I want to ask you is that I mean, it's a bit related to what we are talking about. Uh, how to learn, what problems to work on. I mean, this is something that a lot of people struggle with, especially the young people. That how to choose good problems to work on. Do you think that one inevitably learns this as you get older, you get more experienced, or is this something that you can learn even at a younger stage?
So my advice is that, so academic career is something that takes sometimes a toll personally. You gotta move countries often. It can be difficult in many ways. So to me, my opinion, is only worth it if whatever you're working on is interesting, it's fun, and it's something you care about. So what I would advise is that people try to look for problems they find interesting. Okay, whatever it is, but it's a problem you find interesting, you want to think about. Now, I also think it's very, very good, because they are intrinsically interesting, to think about the big problems. Okay, so I think
Hmm.
there's this quote to Nima, which is like, one should think about the cosmological constant 15 minutes every day. Okay, so I don't, I unfortunately I cannot say I think about it 15 minutes every day. I maybe pack it up in 1 hour at the end of the week or something. But I really try to. You try. It's good to stop and think about big problems. Okay,
Hmm.
even if you're a student, because we honestly, as a community, we oftentimes have no clue. Okay, if we knew exactly what to do to solve the hierarchy problem, cosmological hierarchy problem, electroweak hierarchy problem, the big problems in string theory and any other framework, people would have done so already. There's proposals, there's many proposals which are appealing in many ways, but we really have no idea what is the actual solution to the big problems. It can come from you, it can come from anybody. Okay, it might
Hmm.
just be that you need a different perspective and maybe you get it. Even if not, that's what it's really about. Okay, we are really trying to push frontiers of knowledge, and to push frontiers of knowledge, you have to be ambitious. You have to try to think about big problems. Maybe it's high temperature superconductivity. Doesn't have to be like, like cosmology. Those are the ones that I like more, like cosmology and stuff. But whatever, try to think about the big problem. Maybe you'll solve it, maybe you won't, but you will learn a lot about it just by, because you will think and then say, oh, maybe I would read like this and like that. Has anybody done anything like that? You read a paper, and
Hmm.
the thing is that you're motivated, that you're enjoying that. That's very, very important. Okay. So whatever you do, try to work on things that you find interesting. Now, of course, you cannot spend your whole day just thinking about the cosmological constant problem. You need to find also concrete projects, and that's another skill that you will develop over time, which is find
Yes.
projects in the intersection of interesting and
Doable.
but
Yes.
my advice is, if you went through the work of understanding something and you understood it, okay, it might be worth, putting together like a little short note. It's like, not every paper that is written has to be, the Principia Mathematica. Okay, so it can also be, so maybe you write something that you put together things that are known, let's say. So you start thinking about something, and by the time of that you're done, you realize that all the pieces for that sort of were already in the literature. Still put a note. You made an effort, you understood it, it's going to be good for you. And maybe your unique way, because that's going to be unique, your unique way of putting together things might be also helpful to others. And I know many such instances. Okay,
I see.
so that can also be very, very helpful.
So, um, if I understood correctly, you're saying that if you just start to put together things that are known in the literature, that process may give you ideas for projects. Is that
It
what you're
may
saying?
it may give you ideas for projects, but also like, I don't know, for instance, like uh I cannot come up with a good analogy right now, but um sometimes you start learning about a problem and you start, maybe you figure parts of it yourself. And then once you have figured it out, it's much easier to find things in the literature. And you find that, oh, so I did this calculation, but this was already done in this guy in the 60s, but for a different problem.
Mm-hmm.
And somebody else did this, but for a different story. So in some sense, you could say, oh, but everything is already in the literature. Sure, but you putting it together in a simple package, clear paper, you should try to write clear papers, can be
Mm-hmm.
very, very helpful for the community. And sometimes presenting new things, old things in new languages can lead to massive progress. An example of that is this idea of generalized symmetries.
Mm-hmm.
All the
Yes.
story of symmetries, thinking about the generalized high-form symmetries as topological operators and the like. Um, you can read about most of that in papers of Toft, in some sense. Okay,
Yes.
Wilson loops, so on and so forth. Now, the 2014 paper of Gayotto Kapustin, Cyber Willett, which
Mm-hmm.
introduced these generalized symmetries, it had a few new results, but most of it, in some sense, was like a relabeling, a repackaging, a new language to talk about symmetry. It triggered an explosion. Okay,
Yes.
even though most of the results were, in some sense, in the literature.
Yes.
So sometimes just presenting things in a new way can be extremely helpful. So
Do you think?
what I'm saying this is that the reason why I'm saying this is that oftentimes you find like younger researchers that they made a lot of effort, they figure out some problem, and by the time they're
Mhm.
done, they don't think it's that interesting. They say, well, if you put together A, B, and C, it's already in the literature and stuff. So I just want to encourage to anybody like that who might be listening to us to wrap up the thing, put it in an archive. The worst that can happen is that, you know, some people think, yeah, I already knew this. I guarantee to you there will be readers that didn't know it.
Yeah, of course. I think that's very true. So there's one question. I think I kind of know the answer to that question, but I'm asking this question because I know that some young people have this kind of question. So this example that you gave, the generalized symmetry paper example, do you think that if that paper was written by a young researcher, people would have taken it seriously?
Hmm. I think the I think it would have been harder,
Yes.
in the sense, or it would have taken longer,
Okay.
uh, and it would have been okay. I think yes, I think it could have, but it
Okay.
is not certain. So, but that's okay. Look, the thing is that the sociology of it, we are not. So, what it certainly would have happened, it might not have become such a widespread thing, but I think
Mm-hmm.
a lot of people, or some people in the community, a good chunk of them would have learned about the paper and would have found it very interesting. And I know examples of papers that have done that, maybe uh,
Okay.
for small communities. So the thing is that, you know, when the problem is really that people time is finite. There's a lot of papers in archive every day.
Mm-hmm.
So, if there's a paper by a very well-known researcher that people respect, for sure that one contains very good non-trivial stuff.
Mm-hmm.
Okay? So you're gonna stop and read it a little bit. I'll just look at the abstract, maybe if you're very busy. If the same paper is written by a younger researcher that you don't know, you might erroneously filter that one out because you don't know the person and you have to go to a meeting. That's the only reason.
Yes.
If you had infinite time, you would go through all the papers and you would say, well, this is an amazing paper. Okay. So what that
Mm-hmm.
means is that if the same paper is written by more junior researchers, it might take longer for it to become well known. It become more like word of mouth. So you will go to conferences and say, "Oh, did you see the paper of such and such? That's a very nice language." Yeah, I think if some other people would have written that paper, it would have reached, I think, you know, order of magnitude the same impact. I think it would have
Mm-hmm.
taken longer.
Longer. I
Yeah.
agree, actually. I actually agree with your answer, and this is the answer that I had in my mind. But this is a discussion that I had with some of my younger colleagues, and they were having these kind of reservations. That's why I asked the question.
But I think that's the wrong framing. If you think
Hmm.
that the reason why you should put out a paper is because you think it's interesting,
Yes, I agree. I
not
agree.
because what other people might think or might not. You don't control that. You don't know what that is.
Hmm.
So if you did hard work, also I'm not encouraging people to just put out whatever comes to their brains, write the paper in 5 minutes, and go for a beer. I'm
Yes.
not saying that. But if you
Sure.
spend time on a problem, you thought it through, and you go through the extra effort of putting it together in a readable, reasonable way, okay, why not? If somebody doesn't care about it or they're not interested, that's their business.
Sure.
It should be out
Okay,
there because you are interested in it.
I agree. Okay, so I think the second last question that I have, and then I have some people's questions, right? So the second last question that I have is that what are the qualities of a good PhD advisor? What do you think?
What are the qualities of a good PhD advisor? So I think they should listen to you.
Mm-hmm.
They should be engaging, I think. I think it's also important that to some extent they're kind, because during the PhD it can be hard times. Because of what we were saying before, it's the first time you encounter this kind of challenges that can be tough. Sometimes there's a bit of time pressure because you gotta do the PhD in whatever number of years, right?
Mm-hmm.
So it can be situations where where it's tough, where the PhD can become tough, and so you want an advisor that will be respectful of that will be more or less a kind person or an understanding person with that kind of things. The material advice that I can tell anybody listening to us, which I think is very useful, is before you take on a PhD position, find out about the advisor. How do you do that? Ask. Who do you ask?
Mm-hmm.
Former students, current students. You also go and inspire and check, okay, the last 4 students of this guy quit the field immediately after. Maybe not the best sign. They're all full professors at Harvard, Princeton, Yale, and Stanford. Yeah, go with that person. Okay? So try to figure out and also talk to current students and to former students. Is this a nice person to do the PhD with? Is he supportive in, or she is? Are they supportive in which ways? In which ways are they not? Etc. Okay.
I see. And there is one question that, a lot of my listeners, ask me to ask in every, episode that I do. And that question is that what features do you consider before taking a PhD student?
Which features do I consider before taking it? Mostly, so sometimes the thing is it can be difficult to judge sometimes
Mm-hmm.
when you meet someone one on one. So I can tell you what I look for. So mostly I look for an impression that this is a person which is enthusiastic about the field, about working in more or less the area of things that they would be working with me, so that they're
Mm-hmm.
interested. And that's also has to do with the other thing that we were saying. If someone is really truly enthusiastic, when they hit a difficulty, they're gonna keep pushing. So what you look is someone when they find a difficulty, they will be like, okay, well, this didn't work. What can I do? They want you want someone who ideally would be a bit more independent, that they will try things on their own, and
Mm-hmm.
then for discussion they will come and you discuss what has been tried, not just like I found this and well I don't know what to do. If that's what happens, that's also what happens. It happens to me all the time, honestly. But what I think is most important is ambition. Okay, and I think it's also important if they are engaging with others. These are things which are difficult to measure, and it's even things that vary on a same person. Like you just have a personal problem and then you're not feeling very engaged in that month, maybe the month after your whatever. But someone who's engaging, it's also going to be easier for them, because in academia, people sometimes think that doing physics is all about just sitting in your room and doing calculations. Nothing could be further from the truth. It's a very social field. So you learn a lot from talking to others, from discussing with others, from engaging with others. So I'm also looking for students which I get the impression they're going to be engaging like that, and engage with
Mm-hmm.
the life here at IFT and also at conferences.
So, do you expect your students to be, independent in the sense that they should come up with their projects, or do you give them projects?
No, that depends on the student. That depends on what they want to do, and that's not really even like a very well defined question, because imagine.
Mm-hmm.
So typically when they start a PhD, I give them a project. Okay,
Mm-hmm.
they are of course for me in my case they are absolutely welcome to work with anybody else they like.
Mm-hmm.
Okay, they have their own projects, work with anybody else. That's absolutely fine. Of course, because if an advisor tells you that's not fine, I think that's a bit of a red flag.
Yes, I agree.
Um, But yeah, no. Suppose they're working with me. We start with some project, and then they think it's the most interesting thing ever, and they keep on working on that and that and that and that. I hope that's fine. That's a personal choice. It turns out they were lucky and they started a project they loved and they kept working on that. Some other students might not like so much the project they start with, and they end up with their own ideas. Then that's also great. It is true that you need to develop independence, but that's something you develop throughout the PhD and beyond. Like when you go on postdoc, you're still not fully independent. Oftentimes, you work with your local boss at where you're hired as postdoc. Sometimes with existing collaborations. So you need to build independence, but you don't need to build it overnight.
Right. But what about the case when the advisor says that you can work with anyone, but right now I don't have a project with you, a project
No,
for you?
I think it's always good to have a project going, because it's very difficult when you just started. You don't know the literature, you don't know the field. It's like, what project are
Yes.
you going to find? It's hard. I think that's part of the part of the advisor's role is to find a project. Okay. What I usually do is I try to give choices between. So I oftentimes have the opposite problem. I have too many projects. So what I try is to say, okay, there's option A, which is probably going to be harder, but if we get it, it's more groundbreaking, and option B, which is perhaps not so groundbreaking, but still interesting, and it's perhaps more straightforward. And different people make different choices.
Right. And one more thing that I want to ask you is that, in this dynamic, when you have collaborators and you're working on projects, and even when you don't have collaborators, when you're, working on single author papers, for example, how, do you normally put deadlines? Because otherwise, projects can get longer and longer and longer. And
I,
how productive is it to put deadlines?
that's a tough question, because I think one
Yes.
should put a lot more deadlines, but I'm bad at it. Yeah. So for me, usually when the project is with other people, I'm better at setting up and obeying deadlines, because you care more about it's other people particularly when it's with junior collaborators.
Yes.
Those are the ones I push the most. But then you have a solo. If I have a solo project right now, so I have a couple right now, they're not advancing because I'm focusing a lot more on the others. Deadlines, I think, can be good to the extent that they are realistic, because you run the risk of, if you set yourself 5 deadlines and you jump through all of them, because they were not realistic, you're not going to obey the 6th, right? So what I try to put is more like milestones. It's like, so let's try to have some like vague deadlines, like let's try to have this done by the end of the month, and so it's
I
just you
see.
try. And honestly, for me, what works better is external deadlines. Sometimes you have to do something before, because you're coordinating with some other group, or because the summer conferences are coming and you need to finish it, that kind of stuff. And
And
that's when
sometimes
that
there are,
really motivates me. Yeah,
yeah, sometimes there are journal deadlines as well, right?
that reminds me, I have one today.
Okay, I think that then I should let you go after some time.
I'm,
Then
I'm
probably
fine.
you have.
I'm good with time. So
Okay, so
since we're talking about that, something that maybe some of your listeners you don't know, if it happens like it happens to me today, that you have a deadline today for a journal and you don't have it, you can ask for an extension. They will usually
yes.
get it, which is probably what I will do. Uh, so keep that in mind. You can always ask. Always, in general, don't do something because don't stop doing something because you were too afraid to ask. You always ask. The worst that can happen
Yes.
is that someone tells you no, and that's fine.
Yes, that's true. I mean, if I hadn't embraced that rule, I wouldn't have started this podcast because I had to ask people to come, right? That's why.
That's right. You're certainly one person to which I don't have, I'm preaching to the choir here.
Right. Okay, so I have two questions from the people. One question is that is there a swampland conjecture that you find surprising? If yes, then why?
See, that's a great question, because whatever you find, you might find surprising something the day you find them.
Mhm.
After 10 years of working on it, you're at least become used to it. So, for instance, I remember one of the reasons that I started working on Swampland is because I found this no global symmetries idea that charges lost universally in black holes. I found it I found it surprising that you could get something to low energies. Um, so that one was very, very surprising. So that's one very surprising Swampland conjecture.
What
Let-
about the De Sitter conjecture? What do you think about that?
So the de Sitter conjecture, it's so there's the Swampland conjectures. I told you they were based more on black holes sometimes, and sometimes they're more like based on string theory evidence. The de Sitter conjecture is essentially a codification, an encoding of the observed fact that in the asymptotic regions of this moduli space we're talking about, you do not find controlled de Sitter vacuum. That's why constructions, this proposed de Sitter constructions like KKLT or LVS, they are at the boundaries of control. They are like not really in the asymptotic regions. So the no-de Sitter conjecture is estimated about asymptotic regions. It doesn't say that there's no de Sitter deep in the moduli space.
Right.
So, so I think as a statement about asymptotic things is true. I don't think it's a general proof, but I think it has a lot of evidence. I think it's probably true. To me, it's perhaps not the most. I mean, it's an interesting and it's important conjecture, but it's all in a negative way because it tells me where not to look for the sitter. I'm not going to waste my time looking for synthetic de Sitters. I'm going to try to find them elsewhere when I'm looking for the sitter.
Sure.
Yeah. So, but surprising Swampland conjecture. Well, okay, maybe here's one. I mean, it's a variant of the non-global symmetries, but for instance, the idea using the non-global symmetries, you can argue. There's a 2010 paper by Banks and Cyber, which is just beautiful. You can argue that there's no non-compact gauge groups in quantum gravity. So there's no R gauge groups, for instance. And the argument for that is that if you have a R gauge group, you should have particles with charges, let's say 1 and square root of 2. And then particles with square root of 2 can never decay into a bunch of particles of charge 1. So effectively, there's an effective new global symmetry, which is square root of 2-ness of the charge, which I thought was cool.
Okay.
That kind of thing, I think, is cool. It's surprising, perhaps.
I see. Okay, so the last question that I have from the people, well, actually, it's not a physics question, but the question is that what is your favorite restaurant in Madrid?
Wow. Oh, I should have thought of some place to endorse, and then I get a good.
Sure.
My favorite restaurant in Madrid. The thing is that there's too many. Madrid's a huge city.
I'm sure there.
Wow. Okay, I can tell you. I won't tell you about a restaurant that I've been to recently, but a restaurant that I heard many good things about from the IFT students actually. And we have a large group of string theory students, and there's a consensus. Many of them are Italian, which is relevant because there's a consensus that the best pizza place in Madrid is called Fratelli Figurato. So that one is that's what the students say. So I gotta try it. They say it's very, very good. But
sure. Do you have a restaurant for Spanish food, that you like?
Well, I don't know. Honestly, the best thing to do if you're looking for Spanish food, you go to Madrid, go to a bar, and ask for. So what I like is like little bars, like little tapas bars. For instance, there's one I like a lot, which is close to Plaza de España in one side street, but that doesn't tell you anything since I don't remember the name of the street. I know how to get there, but I don't remember the name of the street. So the way tapas bars work in Spain, you might think that it's something you pay for, but it's really not. Like traditional tapas were originally a worker's meal. So what happens is that you go to a tapas bar, a real tapas bar. You go there, you order a beer, and you get a small beer, and you get a plate, and that plate is the tapas. And the tapas could be anything. It could be tortilla or something other typical Spanish thing, or it could be chicken wings. But a tapas meal is that you start ordering beers one after the other, and then you get different tapas.
And you don't know what's going to come.
You don't know what's going to come, but you know that the more you order, the better it's going to be. So, and in the end, it's a very cheap meal, and it's fun, and there are some very good bars, I think, in Atocha region and in Plaza de España. I know a bunch as well.
I see.
Just go to a small bar, not in the touristy areas. That's the key word. Small bar, not touristy areas.
Okay. So I think my questions are over. Thank you so much for your time. It was great to talk to you.
Thank you so much for having me. It was a pleasure, and it's a pleasure talking to you again. And
no problem.
Really, thanks so much also for the interest in what I do.
Okay, no problem. I mean, that work is interesting, so I think it's hard not to get interested in that. Thank you for your time. I think we will talk again. So if you like this video, give it a thumbs up and consider subscribing. And the YouTube algorithm thinks that you will also like this video.